I'm Umesh Wagmare, and on behalf of the Indian Academy of Sciences, I'm delighted to welcome you today here to the lecture by Jubilee Chair Professor Prof.Ali Nesin. He is Jubilee Chair Professor of the year 2021, and this is his second lecture, and the lecture is on creating infinitesimal. So a brief introduction to Professor Ali Nesin. Professor Nesin is an academician at Istanbul University, founder of the Nesin Mathematics Art Philosophy Villages, director of the Nesin Publishing House. In addition to mathematics research, department chair and Nesin Foundation Management, he also works on oil painting, drawing, portraiture. He is the founding member of the Turkish Human Rights Institution Foundation. Professor Nesin received his doctorate in mathematics from Yale University, and after that he has worked at a number of academic institutions which include University of California, Berkeley, University of Notre Dame, University of California, Irvine, and also the Bilkent University in Turkey. Professor Ali Nesin has been awarded with the Lavati Prize 2018 in recognition of his outstanding contribution and great achievements towards increasing public awareness of mathematics in Turkey, especially because of his tireless work in creating and developing the mathematics village as an exceptional, peaceful place for education, research, and the exploration of mathematics for people. I'm delighted to have Professor Ali Nesin with us. And again, I repeat, his second lecture today is on creating. Over to you, Professor.
Thank you very much. I'm honored to give a lecture to Indian students. I will talk about calculus, or my adventure with the calculus. When I was in high school, I started to learn calculus in high school when I was 17 or 18 years old. And I was in a good school, or I thought so, and I had a good teacher. Oh, I thought so. I had good books. I thought so. But when I started calculus, we had the definition of dy over dx, the derivative, dy over dx, where y was a function, y is equal to f of x. This was defined by limit when delta x goes to 0 of delta y over delta x. You probably know this, of course. So here's a function, and this is x. You take some increment here, delta x, and here there's difference delta y. So this was delta y over delta x is just the slope of this lines of the secant of this line, and then you take the delta x goes to 0. It was fine. It was fine. I had no problem with this definition. And they also sometimes write limit when h goes to 0 of f of x plus h minus f of x over h, where this h is really delta x. It was fine, except that I don't like this dy over dx, you know, and no, I learned this as not dy over dx, but something like, I write in Turkish, dy over dx, as it were only one word, okay? This notation was fine. This notation I had some trouble, but I can accept it as I read this as one word, dy over dx, one word, okay? And the book continued with, I said, well, then they say, then dy is equal to f prime of x times dx. Okay, so I write my exclamation mark. This is mine, not the book's. Well, what does it mean? And they start to explain what dy was. They call this differential. This dy and dx, they call differential. They said they are infinitely small, infinitesimals. There were words like infinitesimals. I read this subsection of the book maybe 50 times to understand it. And I couldn't understand. So I went to my teacher. I said, what are these differentials? Please explain to me. And he started to explain. I couldn't understand. I said, I don't understand, sorry. He repeated. And then he repeated again because I couldn't understand. Then finally I said, okay, fine. There's nothing to do. I don't understand. I knew that there was something wrong in all these things, in all these definitions. I knew I was good enough to understand this. That this wasn't really my fault, but they were unable to explain to me. And then I went to university, college, 4 years of college, and then I went to graduate studies. There I learned that my teacher, my high school teacher, could not explain to me what these were. Because and the book neither, because probably they didn't know what dx dy was really. And now today I will try to explain to you what these things are. Okay. These differentials, they came into history mainly by Newton and Leibniz. Independently in the 1660, something like this, and 1670, something like this. But the idea exists before. Actually, they spoke infinitesimals before Newton and Leibniz. Actually, there's a big controversy over who discovered calculus first. Not first, but they accused each other of stealing each other's result. Now it's considered they did it independently, but in fact they did it independently, but they both borrowed the idea from someone called Barrow. Barrow was somehow the teacher of Newton, and he wrote a book on these things. Actually, he lectured. He gave some lectures. I believe it was in Cambridge. In Cambridge, he gave something like 20 or 25 lectures in total over 6 years. And a few of these lectures were about calculus that didn't exist at the time. It was his ideas. But before Barrow, the infinitesimals existed at the time of actually even Fermat, Descartes, actually, and others. And actually, these people discovered differentiation, derivatives, tangent line. They knew how to draw tangent line. Barrow also. The drawing tangent line to curves were important at the time. They didn't know how to do it really. Fermat and Descartes were able to draw tangent lines to some curves by exactly the same method. What they did is the following. Actually, Newton did like this. So for going back to this definition, he said, okay, let's say you want to define the derivative of x squared. And Newton actually wrote like this for derivative. And Leibniz, I believe he did this. He would do the following. He would take x plus some very small number, not even a number, an infinitesimal. And he called infinitesimal O. Leibniz called infinitesimal O. O is infinitesimal, and why is it O? Now we would write it epsilon. We write epsilon now. But at the time he wrote O, I believe because he thought that O looks like 0. It's not 0, but it's very close to 0. It's infinitesimal. Whatever it means. Minus x squared over O. Like x plus h squared minus x squared over h. And then he computed this. This is x squared plus 2 times xo plus o squared minus x squared. Actually, even in my high school book, it was something like this. Divide by O, you simplify the x squares, and then you have 2xo plus O squared over O, and then you simplify the O's, you have 2x plus O, but this infinitesimal, it doesn't count, so this is equal to 2x. Okay, this is how it did. Actually, also Fermat did similar things. So these discovered derivatives. Integration was discovered much earlier by Archimedes or even other people before Jesus, 400 years before Jesus. Integration was much earlier. I don't know. I'm not sure. I'm not a historian, so probably let's say 300, just something like this. Well, not integration, theoretical integration, but to calculate the volumes of cones or spheres and so on, or to calculate some areas. And what did Newton and Leibniz did? What did they do? They found the relationship between integration and derivatives. They found out that derivative and integration are inverse operations, so-called fundamental theorem of calculus. Actually, Barrow did this before. Barrow really stated the fundamental theorem of calculus and proved it. Actually, Barrow gave his lectures from 1663 to 1668, I believe, and Newton discovered these things at the same time. Not discovered, but he knew he followed Barrow's lectures. This was known. And Leibniz bought later on Barrow's lecture notes. They say. They are not sure about this, but they say. They believe. So Newton, in his note, he said, he was aware that differentials, that infinitely small, was not really sound. It was imaginative. It didn't have any scientific reality. He was aware of this. So he said, what we are reading here are not really proofs of statements. These are only methods or explanations, something to this effect. He said something to this effect, that I'm not really proving something. Don't believe that you are going to find here rigorous proofs, but these are just explanations. Anyway, so Newton and Leibniz discovered calculus, and they spoke about infinitesimals, both. Leibniz introduced the notation integral sum, from A to B, say. This was Leibniz notation. And dy over dx was also due to Leibniz also. And so they published, both Newton and Leibniz, and people started to complain. They said, what do you mean by infinitesimals? What is it? Well, I mean, what is infinitesimal? You have a real line here, Infinitesimal is, first of all, let's say positive infinitesimals. It is, an infinitesimal is called epsilon, is greater than 0 for 1. It's greater than 0. And it is less than 1. It is also less than 1/2. And it is less than 1/3. It is less than 1 over n for all n. But they said stop here. What do you mean? It's less than 1 over n for all n. There's no such number because there's something called Archimedes Principle in the real line that says that you cannot have infinitesimals. And so they said, just imagine that there is such an epsilon. By the way, I'm paraphrasing. I'm just telling you a tale. It's not a history. Just imagine that there's something very, very small, extremely small, so small that it's less than every 1/n. Well, they were not happy. Mainly the English scientists. They were not happy. There was someone called Berkeley. Berkeley was a philosopher, and he was a very deep believer in God. And he was actually he was very religious, and he was actually a priest. Berkeley was then criticized because in his writings he took for granted the existence of God. They said, well, you are imagining things. You are imagining that God exists, and then you follow this idea and you arrive at some conclusions. How do you know that there's a God then? And then when these infinitesimals appeared, Berkeley took this opportunity to write a book. I forgot the name of the book, but there's something called geometry, discussion with the geometry or something like this. There he argued, listen, he said, you criticized me over the years for accepting something imaginary and taking the consequences of this acceptance. But now you are doing the same thing. You are imagining that there's something infinitesimal, there's something called infinitesimal, and then you take its consequences, you accept its consequences, and you think that it's the truth, it's the reality. I mean, you are doing the same thing as I'm doing. It was a very clever argument, of course. And there was a big controversy over philosophers and scientists at the time, whether the infinitesimals exist or not, and what they are. Newton didn't care. Newton didn't care about these issues. Newton was more interested in alchemistry, transforming the cheap metals into precious metals. He was more interested in alchemistry than in philosophical issues. But Leibniz, who is a philosopher by education, Leibniz started math much later, when he was 25 years old. Newton was much younger when he started to be interested in science, in physics, and in math. Leibniz was very much interested in this problem of infinitesimals. He tried to discover a method. He tried to discover a universe like real numbers where infinitesimals existed really. Yeah. In real lines, in the reals, there are no infinitesimals. There is no such number. But potentially, there is such an epsilon. Look, let me write all the conditions. Not all of them, of course. And so on. So I want an epsilon like this. I want an epsilon that satisfies these infinitely many sentences between 0 and 1, between this, and so on. Well, I cannot, of course. In the real line, you cannot. But you can satisfy these. This is, take epsilon to be 1/1001, for example. So infinitesimals potentially exist. In R, in the real lines. They don't exist, really, but potentially they exist. There's always a hope. So you want to satisfy this. Well, you can satisfy up to here. You can satisfy any finite number of these sentences, but you cannot satisfy all. So potentially, there's an infinitesimal. Not itself, but potentially. The idea is there. You know, in math, whenever there's something like this, whenever something potentially exists, but it's not there really, then it means that in some other universe, this object exists. Yeah. For example, suppose you want to solve x plus 1 equal to 0. In Z. In Z, it's easy. You say in Z, it's easy. Then you say x equal to minus 1. Okay? So suppose you want to solve now x plus 1 equal to 0 in natural numbers, positive numbers. And they say there's no solution. Yes, there's no solution, but potentially there's a solution. And what's the solution? Well, you say this x, if it exists, then it must be odd. So that's like 1 plus 2 times something. 2 times something. This x is, okay? And then you solve this modulo 2, the solution modulo 2. Then you solve modulo 4, sorry, modulo 4. You see, modulo 4, this number must be 3 modulo 4. 3 plus 1 is 4. Plus 4 times x2. And you keep doing this, modulo 8. Okay, so potentially x should be something like 1 plus 2 plus, okay? Potentially x is like this. Well, this is not a natural number, but it's called a two-adic number. It's like, suppose you want to find, okay, suppose you want to do the same thing with modulo 10. Well, look at this number, 9, 9, 9, 9, 9. Normally, a natural number stops like this. But keep going this and add 1 to it. This is your x. This is 9 plus 1 is 0, 10. There's 1 here, 10. There's 1 here, 10. So you get 0, 0, 0. As you see, this plays the role of minus 1. In some other system, actually, this is in 10 adic numbers. This is equal to minus 1, really. So this minus 1 doesn't exist in natural numbers, but it exists potentially. You can solve x plus 1 equal to 0, modulo 10, modulo 100, modulo 1000, and so on. And modulo 1 you cannot solve. Modulo 0 you cannot solve. But you see, potentially it exists. So this is something I believe very deep, very philosophical, and very important. If something potentially exists somewhere, then this object exists, maybe not there, but in some other universe. Okay, so let me first talk about real numbers. What are real numbers? Axioms of real numbers. What do I mean by real numbers? I mean a set. You have addition, a binary operation. You have multiplication, a binary operation also. You have order, total order, compatible with addition and multiplication. That's it. And if you want to, 0 and 1. Okay. What do they say? They say x plus y plus z. This is associativity. X plus y plus z. And other things like this. X plus y equal to y plus x. And x plus 0 is equal to 0 plus x is equal to x. And for any x, there's a y such that x plus y equal to 0 and y plus x is 0. So this y is minus x really. And this is with addition. With multiplication, you have similar things. And xy equal to yx. X times 1 equal to 1 times x is equal to x. And now for this, for any x different from 0, there's a y such that xy equal to yx. These are about multiplication. And now something that mixes addition and multiplication, the distributive law, y plus c is equal to xy plus xz. Left and right, but because it's commutative, I only write this one. And 0 is different from 1. Okay, so this is called a field. So this is a field. Real numbers is a field. And now the order, we say, well, x is less than or equal to x. If x is less than or equal to y and y less than or equal to x, then y is equal to x. And if x is less than or equal to y and y less than or equal to z, then x is less than or equal to z. This is an order. This is an order. And for all x, for all y, either x is equal to y or y less than or equal to x. So this is a total order. And what about the relationship between order and addition? If x is less than or equal to y, then x plus z is less than or equal to x plus y plus z. And if x is less than or equal to y and z is greater than or equal to 0, then xz is less than or equal to yz. Okay, this is called an ordered field. All this is called an ordered field. You have too many ordered fields. Real numbers is one, rational numbers is another. There's one more axiom for the real numbers. There's one more axiom. And this is called subaxiom. It says if x is non-empty, subset of real numbers, and if x is bounded above, so x is something like this, so this is real numbers, x is a subset, and it's bounded above. There's a natural number, there's a number which is greater than all the elements of x. It's bounded above, it doesn't go above some number. Then x has a least upper bound. See, this is an upper bound. M is the upper bound of x, but you can find smaller upper bounds, of course. And they say that there's a least upper bound S. Okay, this is very important. So axioms of real numbers is all of that. And there's a theorem that says that there's essentially only one system that satisfies these axioms. Only one system. Not one system, but they're almost the same. It's like if you have two models of this, two structures that satisfy these axioms, then there's a dictionary between them. Like one of them could be English, other one could be French. Here, instead of one, French say un. Instead of zero, French say zero. There's a dictionary. Instead of plus, French say plus. So there's isomorphism. Any two models of real numbers, of these axioms, any two models of these axioms, they're isomorphic. What does it mean philosophically? Philosophically, it means that the real number system is really divine. It is canonical. It's like a number pi. Number pi is a constant of the universe. Real numbers is also a constant of the universe. There's a unique real number system. If there were several of them, we were in trouble. You know, if in France they use some real number system, in India they use some real number system, and if they don't correspond, then you cannot have any scientific collaboration. Or even engineering is not possible. But there's a unique system. And there's one consequence of these axioms. This is famous. Can you see me? Yes. There's one famous axiom. This is the theorem. It's called Archimedes Principle. It says that this is the real line, this is 0, and you take a very small number, epsilon, and you take a very large number, a, and the Archimedes principle says that if you add epsilon to itself enough times, if you keep adding enough times, at some point you will go over a. I believe this is also a very deep statement. Already to think about such a statement is, I believe, is something very important. In high school, I was in a religious high school, Christian religious high school. There was a priest, old one, who couldn't walk. I mean, he could walk, but he would walk like this. He would walk like this, very, very slowly, steps of maybe 1 centimeter. But this priest, we will see him everywhere in the boarding school, everywhere. He would go everywhere because Archimedes Principle. The steps are very small, but with enough time, he would be able to go everywhere. So it says, if epsilon is greater than 0 and a is any real number, then there's a natural number n such that n times epsilon is greater than a. It's Archimedes Principle. So infinitesimal is something that in which Archimedes Principle is not correct, because in infinitesimal epsilon is supposed to be less than 1 over n for any natural number n, positive. So n times epsilon is supposed to be less than 1. So you have, if epsilon is infinitesimal, here you have 0, here you have epsilon. For a, take 1, 2 epsilon, 3 epsilon, 4 epsilon. You never go over 1. You can never pass 1. Okay? So in the real numbers, you don't have positive infinitesimals or negative. You have only 0. Only 0 satisfies all these, well, only 0 satisfies all these axioms. Okay. And so Leibniz tried pretty hard. Leibniz and his disciples, his students, tried very hard to construct a number system in which you have infinitesimals. They were unsuccessful, and for good reason they are unsuccessful. They couldn't do it really. But actually, if you don't want your number system to look very much like real numbers, you can construct very easily a system in which you have infinitesimal. See, let me construct this easy way of constructing infinitesimals. An easy way to construct a system with infinitesimals, non-zero. So we can do the following. Suppose I want it to contain real numbers. So suppose you have such a system. Call it S. It contains real numbers. 0, 1. And I want an infinitesimal. I assume that S has an infinitesimal. Let's call it epsilon. Okay? So I want this system to be closed under addition and multiplication. So epsilon is here. If epsilon is 0, of course, you have epsilon squared. Forget about 1 over epsilon. Let us just forget about this axiom. Where is it? Forget about... Oh, I forgot here. The second one. Every x is an inverse. I forgot this. Forget about this one. Then it's called a ring. Epsilon squared. Of course, you have 5 times epsilon, 5 epsilon, of course, somewhere, and minus 7 epsilon squared. Pi is also here, of course, somewhere here, and pi plus and so on. So you have polynomials, like things that look like polynomials. You look at the ring generated by r and epsilon. You call this r epsilon. And now this is also a ring, which looks like polynomials. Okay? A ring with epsilon. Epsilon is in here. So this is too big. Forget about this s. Just consider this part here. This is like polynomials, r epsilon. Actually, it's isomorphic to polynomials. And now I want to see the order here. So I want to take a polynomial, f of epsilon, and I want to say when is it less than or less than, let's say less than g of epsilon. When is it true? Well, this means that g of epsilon, this if and only if, minus f of epsilon is greater than 0. So I want to decide about this. I want to decide about when a polynomial is positive. I say polynomial, these aren't polynomials, of course, these are real objects. Polynomial is something abstract, but it's isomorphic to polynomials. And so let's write this h epsilon with its coefficients. I have h0 here, the constant term, h0 plus h1 epsilon plus h2 epsilon square, and so on. At some point, it stops. Hn epsilon to the n. I want to decide whether when this is true. Okay. Suppose h0 is positive, for example. Here is 0, and suppose let's call this r epsilon here. It's ordered, r epsilon here, and h0 is somewhere here, and I have h0 plus something that involves epsilon. If epsilon is infinitely small, then h1 times epsilon is also infinitely small. h2 epsilon square is also infinitely small. That epsilon square is even much smaller than epsilon. Epsilon square is infinitesimal with respect to epsilon. As we write like this. This means that epsilon is infinitesimal with respect to 1. In other words, any natural number multiple of epsilon is always less than 1. Epsilon square is, of course, will be much less than epsilon. If you multiply this by 2, by 3, by 4, by 5, by whatever natural number, you will never go over epsilon, and so on. So this is infinitesimal. So here is 0. Here you add to it infinitesimal. So you must stay around h0. You must stay here. So it must be positive. Okay. So if h0 is positive, this will be positive. Suppose h0 is 0. If h0 is 0, then you can simplify epsilon. You have all the epsilons here. Epsilon is positive. You can simplify. You have this, and you have -1. Now, if h1 is positive, again, this will be positive. If h1 is 0, then you take it out and you simplify once more. So how do you define? H0 plus h1 epsilon plus hn epsilon to the n is greater than 0. If and only if the first non-zero coefficient let's call this h of h is greater than 0. This is how you define. Okay, now we know that if there's an infinitesimal, if there's a system containing real numbers and infinitesimals, we have something like this also. Now what we do, we take now the polynomials. We take the polynomials out of x, and we define in R of x, define h0 plus h1x plus h to the n, hn x to the n greater than 0, if and only if, with the same condition here. Okay. Now this gives you a ring, not a field, but you can make it a field by taking, instead of taking the polynomials, take the rational polynomials. It means that f of x over g of x. You can extend the order on the polynomials, on the ring of polynomials, to the field of rational fractional polynomials. And now here it's a field. It's a field. It has an infinitesimal, because now x is infinitesimal. Why is it? Let's see. I want to say that first of all, is x is greater than 0? Yes, because this is a polynomial, and the first coefficient the first non-zero coefficient is 1, and 1 is greater than 0. Is this less than 1 over n? What does it mean? This if and only if, of course. Take this over here. 1 minus nx is greater than 0. When is this greater than 0? When the first coefficient, the first non-zero coefficient is greater than 0, and the first non-zero coefficient is 1. So this x here is really close to 0. It's in here. And if 1 is here, you never pass 1 by adding x to itself. 2x, 3x, 4x, 5x, they are all less than 1. Okay, so this is a system. It satisfies all these axioms except for sup axiom. Because it doesn't satisfy this axiom. Of course, if it satisfied this axiom, then we wouldn't have infinitesimal, of course, because of Archimedes principle. Okay, but so this is fine, but Leibniz, I don't know whether Leibniz knew this. Probably he knew this. I'm pretty sure he knew this. He was a very extremely smart person, but he wasn't happy with this because in this system you don't have square roots. Square root of x is positive, but it's infinitesimal. It doesn't have square root. Well, you can maybe put square root. You can change your things, but then you don't have cube root. You don't have sine function, cosine function. You don't have exponentiation. You don't have a logarithm. So you cannot do analysis really. In order to do analysis, you need these functions. So Leibniz tried to find a system in which you had sine, cosine, exponentiation, everything. Everything which is true in the real numbers should be true in this new system. Except, of course, the subaxiom. If the subaxiom is true, then you have only the real numbers. You don't have anything else. As I told you, any two models of this system, totality of it, they are all isomorphic. And they cannot have infinitesimals. But you want what you want? You want to satisfy a system that satisfies these, that is an infinitesimal. Not enough. You want more than this. You want to do everything you do with the real numbers. What do I mean by this? I will explain later on. You see, there's a difference between these axioms and this axiom. These axioms, except for subaxiom, the other axioms, they are all about elements. This x here is not a subset, it's an element. X, y, everything here is an element. So this is called first order axioms. Or statements. First order means that your statement, your proposition, is only about numbers, not about subsets. This statement is not about elements, it's about subsets. So it's not first order. And it's what makes real numbers special, is this axiom. Okay. Now, okay, so Leibniz lived in the 1660s, yes, in the 17th century. And the graduate school where I went, Yale, before I came to Yale, there was someone, a logician, called Abraham Robinson. Abraham Robinson. He died before I came to Yale. Abraham Robinson. In 1960s, I forgot, I used to know the exact date. It's either 1960 or 1963. Somehow, I don't remember anymore. 1960s, say, he discovered the system that Leibniz tried to find so hard. Unsuccessful, of course. It's called non-standard real number system. Abraham Robinson's non-standard. Okay. So we will construct. Again, it's between quotation marks. Let's say I will construct. I will not construct, but you will think that I'm constructing it. So I will tell the truth in the end. Let's say I will construct, but take this word construct as it's not a truth, it's a lie. But later on about this, I will construct a system of numbers. So I will call them not numbers. They will look exactly like real numbers. Exactly in the sense of first order likeness. I want them to be in the first order with the first order statements I want them to be equivalent. In other words, if a first order statement is true in one of them, it must be true in the other one, and vice versa. And they will have, in real numbers, you have sine function. Well, in the other one, you also have sine function. In the real numbers, you have square root for the positive numbers. Here also, you have square root for positive numbers. Okay, and in the real numbers, all squares are positive. In the other one, all squares will be positive also. In the real numbers, sine square plus cosine square is 1. In the other one, you will also have sine square plus cosine square equal to 1. But of course, in one of them, subaxiom is true in the real numbers. The other one is not true because subaxiom is not first order. Okay, so let us candidate for Abraham Robinson's non-standard real numbers. I want my numbers to be sequences of numbers, sequences of real numbers. Okay. Like this. Okay. This will be one number. This is the Cartesian product of real numbers over natural numbers. By the way, instead of taking these natural numbers, you can take any set you want, but it rather be infinite, any infinite set. I'm taking natural numbers here for the sake of it's easier. Okay, and I want to define addition, multiplication, and order. Addition is easy. You add term by term. Okay, if you have a sequence and yn, if you add them, you just add the terms. If you want to multiply them, you multiply term by term. I don't have minus here, but if you want to have minus, you do minus here. If you want to have sine of this, sine of x1, xn, sine of this, you can take sine of each term. Okay. For functions, it's easy. For function, you just do the operation term by term. Okay, nothing difficult. Now the ordering is difficult. The ordering is difficult. I want to order. You see, this cannot be a system like real numbers because here, if you take 1 0 1 0 1 0, these alternating 1 zeros, and you multiply it with 0 1 0 1 0 1, you get 0 0 0, right? You get 0 0 0. All zeros. This is the zero of the system. The how do you call this? It is the invariant for addition. I forgot how we call it. It is the one that element neutre. In fact, neutral element. So you multiply two numbers. This is non-zero. R say and S. R times S is equal to 0, but neither R is 0 nor S is 0. So this doesn't work in the real numbers. In real numbers, it's a domain. Whenever you multiply two numbers, if you get 0, it means that one of the numbers must be 0. And this is a first order statement, right? We have for all x, for all y. If x, y equal to 0, then x equal to 0 or y equal to 0. This is true in real numbers. This is how we write real number system satisfies this. The other one, this one, does not satisfy. Does not satisfy. So one of these must be 0. Either this must be 0 or this must be 0. But they are not. Actually, you can have other multiplications that give 0, and neither of them is 0. So one of them should be 0. Right? But they are not. Let me keep going. For example, I also want let's see, I want an order. So let's take one number, 0, 1, 2, 3, 4, 5, and so on. And let's take another number. I call number, a sequence, I mean. Let's take 1, 2, 3, 4, so on. And I want to decide which one is larger, which one is greater, because I want the total order. Either this must be greater, or this must be equal, or this must be one of them. I have to decide. Well, I want, if you look at my feelings, if you ask to a child, even 7 years old, so which one should be bigger, the child will say this one, because all the terms are positive, right? All the terms, all the terms are bigger. 1 is larger than 0, 2 is larger than 1, 3 is larger than 2, and so on. So it looks like we should have something like this. This should be bigger, intuitively speaking. Or I can do something like this. Three, 4, let's take this one, 5, 6, 7. This one, and let's take another one here. Let's take 1, 2, then 6, 7, 8, 9, and so on. And you ask yourself, which one should be bigger? Well, if I look at the first term, this is bigger. With the second terms, this is bigger. For third term, this is bigger. And from the third term on, this one, these terms, they are larger than this one. The first two terms, well, unfortunately, they don't obey to the majority. The majority says that this one is bigger. Okay, so if I want to be democratic, I should say this is larger. In other words, what I'm going to do is this. Suppose I'm writing a statement about these sequences, and I want to know whether the statement holds or not. I will ask each term, does the statement hold for you? For some of the numbers, for some of the terms, the statement will hold. For some of them, will not hold. So yeah, in other words, they will say, what's this English term for yes and no in Parliament? Yeah or nay, right? So they will say yeah and no, nay, yes or no. And I will say, okay, let's see the majority. What does the majority say? And I will obey the majority. This is the idea. Okay. So I want to define the order. As I told you, one of these should be 0. Let's say 1 0. I'm asking, is 1 0 1 0 1 0 this one? Is this equal to 0 0 0? Is this true? So I'm asking the first term. I start with let's say R0, and this is S0. This is 0. I'm asking, is R0 equal to 0? No. 0 says no. No's and yeses. How do you write yeses? I don't know. No's and yeses. No's, which one? The first term says no. R1, for R1, it says yes, I'm 0. 2 says no. 4 says, the even numbers says no. The odd numbers says yes. Okay, so this is 2n. This is 2n plus 1. So one of them should be majority. Either this number should be either equal to 0 or not. There's no third choice. So either the even numbers should be majority or odd numbers should be majority. So I have to decide what majority means. What subsets of natural numbers are majority? Question. Which subsets of n are majority. Let's call this let M, this curly M, be the set of majorities. This is a set of subsets of n indices. So what will I say? I will say I take a sequence xn, I take a sequence yn. I want them to be equal if and only if the set of n such that xn is equal to yn is in M, is a majority. But of course, these are not equal, of course, right? For these to be equal, I need xn to be equal to yn. They are not equal, but I want them to be equal. In math, whenever you want something, you want two distinct things to be equal, you wish, you hope. But if they are not equal, what do? Then instead of saying they are equal, you say they are equivalent. So this is equivalent relation. This is going to be an equivalent relation. Like if you do if you work modulo 5, 1 and 6 are equal modulo 5. But we don't say equal, we say they are congruent or they are equivalent modulo 5. Okay, so I have to decide about M. Okay. So what properties do I want from M? Suppose X is in N. Okay. And okay, so it means that, so now take this element here. This is the set of indices, right? So indices. If 0, so you take the following number or sequence. You write zeros whenever the indices are in X. The rest take ones. Take ones everywhere. And if I is in X, then let's call this AI. AI is 0. And if I is not in X, then AI is 1. I take the following. So this is the characteristic function of the complement of X. Okay. So this number should be 0 because by 0 I mean 0, 0, 0, 0, 0. Right? Because I ask the first term, are you 0? He says no. The second one, no. But whenever the index is in X, it says yes. Yes. The set of entries that say yes is a majority set because I choose. Oh, sorry. I meant M here. I chose X to be a set of majority. So this is equal to 0. 0 I write like this. Okay. Now take another one. Take a set Y greater than X that contains X, and take the following set. Take the same thing. You take for Y. You take 0 for elements of indices in Y. You take 0. The other ones you take 1. Now, if you multiply these two, you of course get this one. You get the same thing because you multiply term by term. This is X, but X times 0 is 0, of course. It's true in real numbers. It should be true also here. Therefore, this must be 0. In other words, these elements, these indices here, must also be a majority. So if y is a superset of x, then y is also a majority. The majorities should have this property, which is very intuitive, in fact. If x is a majority, and if y is larger than x, then y should also be a majority. It's intuitive. But here we see that it must be so. Something else. By the way, 0, 0, 0, all the way 0. This sequence is 0, so natural numbers must be a majority. The set of natural numbers must be a majority. Okay. Now take two sets, x and y, two majorities. Two sets. And now what do I do? Take this element. What do I want? I want the intersection. So take this element. For x, it's 0 if element is in x. It's 1 somewhere else, everywhere else. And take another element. So this element is 0. 0 because elements, the indices which are in x, they say I am 0. Therefore, majority says I am 0. Therefore, this should be 0. Take a y now. For y, take the same thing. 0, 0, 0, 0, 0. And 1 elsewhere. This is also 0. Because this is in y. Now add them. 0 plus 0 normally should be 0. If you add them here, you get 2, 2, 2, 2, 2. Here you get 1s, 1, 1, 1, 1. Here at this intersection here of x and y, you get 0s, and then you get 1s, and then you get 2s. Okay. This is supposed to be 0. Therefore, the indices of the entries that correspond to 0 should be majority. This is x intersection y. So x intersection y must also be x intersection y must also be a majority. Okay. Well, and also remember, 1 was supposed to be different from 0, and but this corresponds to 0 sequence. This corresponds to 1 sequence. So nothing says I'm equal. So therefore, empty set should not be in M. And M is what's M? M is a subset of P of N, set of subsets of N. Every element of M is an element of P of N. In other words, is a subset of N. This is called a filter. A filter. But I need examples of filters. Examples of filters. Take set of X subset of N such that 3 and 5 belong to X. Let's see. If X contains 3 and 5, any superset of X contains 3 and 5, of course. Natural numbers contain 3 and 5. Empty set does not contain 3 and 5. If X and Y contain 3 and 5, intersection also contains 3 and 5. You can take any subset of natural numbers here. Of course, you can also take set of X in N such that 3 belongs to X. This is larger. This is larger than this one. There are more sets like this. Okay. These are called principal filters. These are easy. These are too easy. Trivial filters. I take something called Fisher filter. Very important, Fisher filter. Fisher filter. Take cofinite subsets. We have seen this. You take, for example, you take 1, 0, 1, 0, 1, 0, and you take 0, 1, 0, 1, 0, 1. When you multiply, you get 0, right? So one of these two should be 0. In this way, you have one more property for any x in n, either x in M or the complement of x is in M. And something now it's called a ultra filter. Okay. And Fisher filter is this is the set of cofinite subsets of N. This is also a filter. And now take any right here. Take any filter, any maximal filter, large possible, and take any maximal filter that contains the Fisher filter. Let's call Fisher filter F0. That contains F0. Okay. Now take the product of natural numbers, of real numbers, and divide by this equivalence relation. This is an equivalence relation. Divide by this, let's call this U. Divide by this U. In other words, say that x is equal to y if and only if the set of n such that xn is equal to yn is in U. Okay? Let's call this R tilde. Now R tilde has infinitesimal. Look at this. 1, 1/2, 1/3, 1/4, 1/5, and so on. This number will is this number less than 1/5? These ones say no, but the other ones say yes. So it will be less than 1/5. So this is infinitesimal. Is this greater than 0? Yes, because each term is positive. And the theorem says that R tilde and R are elementary equivalent. In other words, anything which is true for the real numbers, first order, is also true for R tilde. Okay? Now the question is there an ultra filter? If there's an ultra filter, then there will be a system that looks very much like real number, and it will have an infinitesimal. Is there an ultra filter in the universe, in our universe? Well, yes, if you accept the axiom of choice. Without the axiom of choice, it's impossible to find an ultra filter like this. So, without axiom of choice, in other words, this shows one more why our real numbers is really canonical. Because to construct something else, you need an axiom which is very much, it's very dangerous. Okay, sorry for taking over time.
Well, Professor Nesin, thank you very much for a lecture which covered the history, philosophy, and also very interesting mathematical aspects of infinitesimals. We are thankful, and maybe there will be questions which we may receive by email later. So thank you again on behalf of the Indian Academy of Sciences, and as we said in the last lecture, we look forward to hosting you in the Academy at a time that's possible, hopefully.
Thank you very much.
Thank you.